Hello everybody. In today's videos we're going to be going over how to find critical values algebraically. So this video we have about 10 example problems where we work with polynomials, work with the product rule, the quotient rule, and the power rule, and then the chain rule to help us figure out what the critical points are. And then we have natural log and some trigonometric functions. So if that interests you, stay for the rest of the video. So our definition of a critical value or critical point is a point x comma f of x is a critical point of a function f of x if either f prime of x equals 0 or f prime of x equals does not exist, aka undefined. So what does that even mean? It's basically just saying, hey, if your critical value doesn't lie within the domain of your function, then it can't be a critical value. However, if it does lie within the domain of your function, then hey, that critical number or value is either going to equal 0 or it's going to equal does not exist. Those are your parameters. Those are your only two options. So here we have a written rule. So critical points either occur at f prime of x equals 0 or f prime of x equals does not exist. That's the only two ways. So I'm going to give a brief recap. On the last video, I went into depth explaining increasing and decreasing values and some theorems to help you understand this. So if you haven't watched that video, I recommend it. So I'm just going to do a brief recap of what we talked about a little bit. So our critical values help identify max and mins. So if we look at this graph, we know that E, D, and C points, we have critical values because that is our mins and maxes. So here's our absolute max, here's our absolute minimum, here is our local max, right? So at these points we have critical points. So how did we figure out if our critical points, according to Fermat's theorem, either equaled 0 or if it equaled does not exist, if we're just looking at it graphically speaking, not algebraically? Well, we figured out that if we can make a horizontal tangent line, a unique horizontal tangent line on the critical point, then that means that at those points, f prime of x equals 0. So here, f prime of x equals 0, and down here, f prime of x equals 0. However, if you couldn't make one unique horizontal tangent line, which we cannot do here, we can actually make a bunch of tangent lines there. That means that at that point, f prime of x equals does not exist. You could also kind of ask yourself, hey, is it a sharp turn, a very abrupt turn? Then okay, then it's not going to exist either. You could also think of it with the roller coaster method that I discussed. I'm not going to go through that whole thing right now, but again, if you haven't watched that video, I recommend watching it. So let's just jump right into it. So example 1. So I'm going to list the domains, but chances are your professor or your teacher is not going to tell you what the domain is. They're just going to expect you to know it. So in most polynomials, well, I guess all polynomials really, your domain is going to be from negative infinity to positive infinity. So we don't really have to worry about anything. We just got to worry about figuring out what our critical point is. So what are even the steps to finding our critical points? Well, I have them listed here. So our first step is going to be finding the derivative. Again, I'm going to assume you know how to find the derivative, so I'm not going to show all the baby steps to finding a derivative, or more so explaining the rules. So f prime of x is going to be 2x minus 4. After we have found our derivative, we set it equal to 0. After we set it equal to 0, we factor and then we solve for x. So I'm going to pull out the greatest common factor, which is 2. Then we're going to solve for x. So we're going to only do this because we don't care about this guy. He's not going to give us the x value, so there's no point in touching him. So we're going to take x minus 2, and we're going to equal it to 0, and that gives us 2. So our critical value for this is x equals 2. Now let's go to our next problem. If you want to try this one out, feel free. We have the steps written right here, and again, the domain is all real numbers, so it's not going to be any problems. So let's just go over these steps again. Let's do it in orange this time. So find the derivative. So f prime of x equals 6x to the second power minus 6x to the first power minus 12. Then we must equal it to 0 and then factor it. So that's you can either factor it, then equal it to 0, or simplify it, then equal it to 0. It really doesn't matter as long as you're equaling it to 0 at some point in time and finding your x values. In some complex problems, I prefer to simplify it before equaling it to 0. So it really is just dependent on what your brain likes best. So now that I've equaled it to 0, I'm going to pull out the greatest common factor, and in this case, it's going to be 6. And when I pull that out, I'm left with x squared minus x minus 2. After we do that, we're going to factor it once more. So if you don't know how to figure out what your numbers are going to be within these parentheses, I can explain that really quickly. So you take this number and you figure out what its factors are, and really we don't have many options. It's literally just 1 times 2 is our only option. And we ask ourselves, okay, out of these numbers, out of these factors, which ones, when added or subtracted, give us the leading coefficients value of this polynomial, oh my gosh, of this exponent. So x to the first, right? So in this case, it would be x minus 2 times x plus 1, because when you multiply it, -2 times +1, you get -2, which is right here. And then when you subtract -2 plus 1, you get -1, which is this guy right here. So it works out. That's kind of like a botched explanation. But if you look up how to factor polynomials, like some videos should pop up. Anyways, let's get back to this. All right, so now that we have this, we literally just equal this both to 0 plus 2 plus 2, x equals 2, -1, -1. Okay, so our critical values are right here. It's going to be x equals 2 and x equals -1. Chances are your professor, your teacher is going to have you list them like this. So that's how they'd have you list them. So those are your critical values. And again, our domain is all real numbers, so it fits within our domain. So we do not have to worry about anything like that. All right. So this one we're going to be using some rules to solve. So let's do that now. We're going to be using the product rule. So if you don't remember the product rule, and again, people write it differently, but it's going to give you the same thing regardless in what order you put it in for this. So our product rule is going to be the derivative of the first, so f prime of x to the first times the second plus the first times the derivative of the second. So that's just a little quick reminder. So now let's just do it. So we got the derivative of the first is going to be 2x to the first power times our second, which is x minus 4, plus our first, which is x squared, times the derivative of our second, and our derivative of x minus 4 is just 1. So now that we've found our derivative, let's equal her to 0. Okay, so I'm going to actually distribute this and then try to simplify it because we can pull out those x's. So 2x times x is going to give you 2x squared. 2x times -4 is going to give you -8x. And then we have that plus x2. So let's combine our like terms. So let's combine our 2x to the second power plus x to the second power, which gives us 3x to the second power minus 8x. And now we can pull out that x value. So 0 equals x. We're pulling out the x, remember, just 1. So we're left with 3x minus 8. Now we can equal both of these to 0. And we are going to get, here, I'll show you all the work over here because we're running out of space. So we get 3x minus 8 equals 0. So we must add 8 to get 3x alone. Then we must divide 3 by both sides so that we get x completely by itself. So our critical values are going to be, and I'll list them how your professor or teacher is probably going to want you to list it. So your critical values are 0 and 8/3. And again, our domain is all real numbers, so these fit perfectly fine. Okay, let's do one with the quotient rule. So again, this domain is all real numbers because if you look at that x squared, it doesn't matter what you put in there, whether it's negative or positive, it's always going to spit out a positive because again, it is squared. So the rule for the quotient rule or whatever is this. It's going to be g of x times f prime of x minus, and again, people write it in a different way sometimes. It's going to give you the same freaking thing. All right, so g prime of x times f of x in brackets, then g of x squared, where g of x is the denominator and f of x is your numerator. So let's put it into practice. So we're going to get x squared plus 1 times the derivative of the top, which is literally just 0, minus the derivative of the bottom. The derivative of the bottom is 2x to the first power times f of x, which is literally 1. And I like to use these brackets so I can make sure that I am distributing that negative to everything inside, because sometimes you can get an expression inside those brackets and it's really important to distribute that negative sign. And then at the bottom we get what our denominator is, but we have to square the entire thing. So f prime of x equals this. So let's simplify her. So anything times 0 is always going to give you 0, right? So this completely cancels itself out right there. Then we are left with negative 2x, because 2x times 1 is 2x. Then negative times 2x is negative 2x over x squared plus 1 squared. So something I need to know. So regarding that rule we talked about earlier, it said that f prime of x equals 0 or f prime of x equals does not exist. So right here, we are only going to set our numerator equal to 0, not both. So why do we only set the numerator equal to 0? Because we will get f prime of x equals 0, but the denominator cannot be equal to 0 because then the whole derivative becomes undefined, right? So therefore, that's why you only do the numerator. You do not set the denominator equal to 0 because it will be undefined. It won't work. So our critical values are only going to be in the numerator. So we're going to set the numerator equal to 0. When we do that, we have 0 equals negative 2x, and then we're going to divide, and 0 divided by any number is just going to give you 0. So, well, any number besides 0, right, is going to give you 0. So our critical value here is just x equals 0. All right, so this one, we have to put it in its proper form before we begin, right? So let's do that first. And then, of course, our domain is all real numbers, so we don't have to worry about anything. So let's put her in proper form so that we can take the derivative. So now let's do our chain rule. So our chain rule basically says this. You take your exponent, you put it in the front, you rewrite u, this would be like u, right? And then you subtract the exponent by 1, and then you multiply it by u, by the derivative of u. So d dx of x squared plus 1. So we get f prime of x equals 1 over 2 times x squared plus 1 minus 1 over 2, because if we look at this guy over here, okay, when we make it so that they have the same denominators, we get 1 over 2 minus 2 over 2, and that's just going to give us negative 1 over 2, which is where we get her from, right? Okay, just making sure you're following. All right, then it's getting multiplied by the derivative of the inside, and the derivative of the inside is literally just going to be 2x to the first power. So now let's put that 2x in front because we can simplify her. So when we take 2x and we multiply it to 1/2, we get 2x over 2, right? I'm going to rewrite everything. I'm going to try not to skip any steps so you understand. So 2 over 2 is literally just 1. So these 2's cancel out, and we're left with x times x squared plus 1 minus 1 over 2. So this isn't in its proper form. So let's put it in its proper form because we have a negative exponent, which means it should be at the bottom of the fraction in the denominator. So when we do that, we're going to take this and we're going to put her to the bottom, right? So in the numerator, we're left with x, and I'm already going to set her equal to 0 because she's basically all done. So we have x in the numerator, and then what gets put in the denominator, x squared plus 1 to the power of 1, over 2, right? And then we could also write it as a radical if you really wanted to. So we could write it like this too. It really doesn't matter because we're not even going to touch, we're not even going to be touching the denominator. We're only be touching the numerator. So, I mean, it doesn't really matter if you want to put it in this form or this form. Okay. So now that it's in proper form, let's just take our numerator and equal her to 0. So we get the numerator, which is x, equal to 0. There's nothing to do. So our critical point or value for this function is going to be x equals 2. That's all it is. So let's look at this one. So we have natural log. So remember, natural log ln is only defined for when x is greater than 0. Therefore, our domain is going to be non-inclusive of 0 to infinity. All right, so let's do this. So again, we're going to use our product rule. So the derivative, I'm not going to write it out this time. So we get the derivative of the first times the second plus the first times the derivative of the second. And the derivative of ln x is just 1 over x. So let's just write this all together now. And now we can actually simplify this, right? We could simplify it by 1 power of x. So let's simplify her. All right, she simplified, and we can still simplify even more, right? We can actually pull out that x. So let's just set her equal to 0 already. And let's pull out this x that we see here. So when we pull out the x, we're left with 2 times ln of x plus 1, right? And now we can just set both of these equal to 0 and find out what our critical numbers are. So we just have x equals 0. Then we have 2 ln x plus 1 equals 0. So let's work on this guy. So let's subtract the 1 from both sides. We get 2 ln x equals negative 1. Then we're going to divide this 2 from both sides so we can continue to get it by itself. Then we're left with ln of x equals negative 1 over 2. But if you remember, we have an logarithmic exponential rule. And this rule basically just says ln of x equals a, so x equals e to the a. So we're going to put it in its proper form so we can solve for x. So let's do that now. So following this rule, we're going to get x equals e to the negative 1/2. And then we can take it even a step further by putting it in radical form. When we put it in radical form, we're left with a 1 in the numerator, and then in the denominator, we have the square root of e. So earlier, I did just skip a step just now. So let me show you, just in case you're lost, okay? So what we did just now, we put this into the log and exponential rule form, and we got this. After we got this, all we did was we took x equals e to the negative 1/2, and we put her in the denominator so that she wouldn't be a negative exponent. And then because we have 1 over e to the power of 1/2, that's equivalent to putting it into a radical form. So then we're left with this. X equals 1 over the square root of e. All right, so let's take a look. Remember, our domain is ln is only defined for when x is greater than 0. So 0 is not inclusive. Therefore, this guy is not a critical value. The only critical value that we have is this guy right here. X equals 1 over the square root of e. All right, that was kind of a trip, but it's good. It's a good example. All right, we're going to do one more. So feel free to pause the video and try this out. I think it'll be really beneficial to get more practice in using natural logs. We'll find the critical values of natural logs. So let's just get started. Again, we have the product rule. Derivative of the first times the second plus the first times the derivative of the second. So we get, oh my gosh, we get f prime of x equals ln of x plus x over x. And x over x is literally just 1, right? So f prime of x, for the love of God, please do not write ln of x plus 0. That's not correct at all. Okay, it's going to be 1 because you have a 1 over a 1. It's basically what that is. In front of a variable, even if there's no number, there's an implied one. We just don't write it. So we have f prime of x equals ln of x plus 1. So now we're just going to equal this to 0 because there's really nothing left for us to do, right? We already found our derivative. Siri needs to mind her business. Okay, so let's solve. So let's get x by itself. So we get negative 1 equals ln of x. And then again, we're going to use that log exponential rule that states, just literally drew an H, okay. ln of x equals a, so x equals e to the a. So that's what we're going to do right now. And actually, before we do that, I'm going to write it, because it's bothering me. I want the x on the left side. Okay, so I just rewrote it. It means the same thing. I just moved it to the other side because it was bothering me. All right, so now that we have ln of x equals negative 1, we're going to use this rule. Hello? There we go. Okay. And we get x equals e to the negative 1. I kind of skipped a step in my head. And then because it's a negative exponent, we want to put that in the denominator. So then we get x equals 1 over e. That's what I was trying to do earlier. Kind of skipped a step there, just in case you wouldn't follow it. But there we go. We get ln of x equals negative 1. We used this guy right here to get x equals e to the negative 1. And then to put it in proper form, we put the e in the denominator so that our exponent could be positive. So does it fit inside of our domain? Yes, it does. So this guy is our critical value, x equals 1 over e. Now let's do example 8. So now we're using the quotient rule for this one. This one's going to get a little messy. So I'm going to try my best to not make this confusing. So we have our quotient rule. I'm not going to write it again. So it's going to be g of x times the derivative of f of x, which is the top. Oh, and I actually forgot to put f of x equals. There we go. Now it's a function. Now it makes sense. All right. So we have x to the 4th power. Ooh, what the frick? F prime of x equals. Okay, so we have the bottom times the derivative of the top. And the derivative of ln x is just 1 over x minus, and again, I like to use brackets, the derivative of the bottom. The derivative of the bottom is 4x to the 3rd power times the top, which is just ln x, brackets. And then we take the denominator and we square the entire thing. So let's keep going with this. So we have x to the 4th power times 1 over x, which gives us x to the 4th power over x minus 4x to the 3rd times ln x, all over x to the 4th squared. Then we can simplify her again. So we get x to the 3rd because there's a 1 here and we have a 4 here. So that means we could take 1 away so that we just left with x to the 3rd minus 4x to the 3rd. And this works out beautifully. So I'm going to distribute that 2 to the x to the 4. So whenever you have an exponent raised to an exponent, you literally just multiply it. So what is 4 times 2? It's 8. So our denominator is now x to the 8th power. So I did this because I noticed these guys right here. And so that means that we're going to be able to pull out an x to the 3rd power and then simplify this even further. So that's exactly what I'm going to do right now. So hopefully you see the vision. If not, you're about to see the vision. So I'm going to pull out the x to the 3rd power, and we're left with 1 minus 4 ln of x over x and x to the 8th. All right. And now we can simplify out this guy and this guy. So I'm running out of space, so I'm going to start writing over here. So we're going to simplify it. So when we simplify it, the x to the 3rd gets diminished from the top. So we don't have her in the top anymore. We're only left with 1 minus 4 ln of x over, and then what is 8 minus 3? It's x to the 5th. That's how many we took away from the bottom and the top. We took away x to the 3rd, so we took away 3. So now we're left with f prime of x equals 1 minus 4 ln of x over x to the 5th power. And that's really all we can do. So now let's set our numerator equal to 0. And again, ooh, why am I writing in white? Let's do it in pink. So let's set our numerator equal to 0. And friendly reminder, we do not set the denominator equal to 0 because if the denominator is 0, the whole derivative becomes undefined. So we only take the top. So let's do this now. We're going to subtract 1. We're left with negative 4 ln x equals negative 1. We're going to divide by negative 4. We are left with ln of x equals 1 over 4 because these two negatives cancel each other out. And then we're going to use that rule, our logarithmic exponential rule, which states ln of x equals a, so x equals e to the a. So we are literally going to just be left with x equals e to the power of 1 over 4. So this is our critical value. And does it fit? Yes, it does. It fits our domain. Okay, we're almost done. We have 2 more, and then we are going to be completely done. So these 2 last ones are going to be trigonometric functions, and I provided intervals because if not, then we'd be listing values forever and ever and ever and ever, and you're going to see exactly what I mean in just a second. So our first rule is to define the derivative of the function. All right, the derivative of sine of x is cosine of x. the derivative of cosine of x is negative sine x. So what I'm literally going to do is I'm going to set this equal to 0. And then I'm going to move sine of x over to the left side. So now we are left with sine of x equals cosine of x. So I did this because now we can find the values. Before wouldn't be able to find any really values, really. So let's find the values. So where on the unit circle, and that's where the interval comes in, because if you look at the unit circle goes from 0 to 2 pi. So that's all we're talking about right now is the unit circle. If there was no interval, you would have to list values inside of the unit circle and values that go on beyond, and that's just an exhaustive list. But it can also be represented in a certain formula. I'm not going to do all of that. I doubt your professor, teacher, whatever is going to make you do that. I'm pretty sure they'll provide you an interval. So if you look at the unit circle, let's see where on the unit circle does sine equal cosine. And if we look, we notice that sine of x equals cosine of x at pi over 4, which is 45 degrees, and then at 5 pi over 4, which is 225 degrees. At those two values, we have it where sine of x and cosine of x equal the same value. So therefore, our critical points, our critical values are pi over 4 and 5 pi over 4 within our given interval. All right. So this is our answer for these, right? And if you were, I don't want to make you pull up like the unit circle. So at pi over 4, we have this value. And at 5 pi over 4, we have this value. So this is sine, this is cosine, right? And at pi over 4, these are equal. And at 5 pi over 4, these are equal because they're the same value. So that's why our answer is going to be x equals pi over 4 and 5 pi over 4. So I hope that helps a little bit more. Hello? Cut. Okay, let's move on to our last problem, yay. All right, so this one we have a natural log and a trigonometric function in one. So let's look at our domain. Well, yeah, let's look at our domain. So remember, lmx is only defined for when x is greater than 0. So therefore, sine of x has to be greater than 0. And our interval is from 0 to 2 pi. But again, sine of x has to be greater than 0. And the only part of our unit circle where sine is positive is from 0 to pi. Non-inclusive of 0, because again, ln is only defined for when x is greater than 0. All right, so our domain is going to be 0, comma, pi. Non-inclusive for either, okay? So let's get started. So we are going to, again, this is a composite. So what we're going to do is we're going to take u prime over u. So our u is this guy. So what is u prime? Well, what is the derivative of sine? The derivative of sine is cosine. So we get cosine of x over u, and u is just sine of x. So it's going to be the derivative of u over u. So that's all we have to do here. And so cosine x over sine of x is just cotangent of x, right? So that's all there is to do. So let's equal it to 0. So then we just have to ask ourselves, this one's a little different from the last one, right? All we have to ask ourselves for this one is, okay, where on the unit circle, because again, our parameters are given here, 0 to 2 pi. So where on the unit circle do we get cotangent equals 0? Well, we get it at pi over 2 and 3 pi over 2, but remember, sine of x has to be greater than 0. Therefore, the only answer is going to be pi over 2, not 3 pi over 2, because 3 pi over 2's sine is -1, and that is not greater than 0. So our only critical value for this is going to be x equals pi over 2. So that is all for this video. We found all of these critical points or values. In the next video, I'm going to be going over how to find max and min values inside of an interval, inside of a closed interval, and then inside of an open interval. All right, so I hope you enjoyed